Hi guys, this is part 2 of the video. It's related to hardware of the solar BMS, and before I go and do that, I will start with how you should connect this solar BMS. I know I already mentioned this in the last video about the user interface, but just in case, I will go once more very fast through the process of how you connect this first time to your system. And not just the first time, but you will probably only connect this once. So what you will do is first you need to connect the battery terminals, not just one. I connect just one in this example because I have just a small ultra capacitor bank here, so it doesn't require high current. And then after you connect all this to your battery, you connect the 10-pin sensor wire connector, and this will power up the solar BMS. Then you go in parameter settings, select your battery type, change whatever it is that you need to change, because these predefined types are just there for guidance, but you need to change other stuff like number of cells and maybe over and under voltage thresholds need to be different in your particular case. You need to study your battery and also know what your system requirements are, and then you push save. You transfer all the data to the main EEPROM of the main IC, and after you do that, you remove the 10-pin connector for at least 5 seconds, reconnect that, and then you go into page 4 of the monitoring to make sure that you disconnect the load. So the charge FET and discharge FET should not be highlighted. And then you connect the load and the PV panels. And that's it. This is just a very short introduction on how to connect this to your system. Okay, and now I will go around the solar BMS to show you what you have in here. It's okay, let's start with a programming connector. I don't know if you can see it. I hope it will focus on this. There is a 5-pin programming connector in here, and the pinout for that, I mean, you will use something like this, cable like this with female header pins, and you can use how many pins you need from here. But now that it's connected, I can maybe you can probably see better pin 1 to 5, and if I take these colors in here, I hope you can see the first one is blue and the last one is black. So the first one, it's the programming clock. Then the brown one, it's the data, also for programming connector. The one in the middle, the third pin, is the ground. It's I think it's gray here. And then you have the white and the black. These last two are X1 and X2 pins that you can use to connect to external relays or external MOSFET or anything like that to extend the power capabilities of the solar BMS, or to connect multiple BMSs in series for larger battery banks. But what you will want to do is use an optocoupler here. If you want to use these X1 and 2 pins, this is optional. It's not really necessary in most cases, but if you want to use external relays or things like that, then you should have here an optocoupler so you don't damage the microcontroller, something like that. And usually the optocouplers have infrared LEDs inside, and these are the I/O pins from the microcontroller directly to this connector. And the microcontroller is supplied with 3 volt, 2.95 or something like that, so 3 volt. So that's what you will get on these pins. Of course, if it's 0, it's nothing, it's ground. But if they are on level 1 logic and are positive, then you will get about 2.9 or 3 volt on these pins. But you should not draw more than I think you can go up to 20 milliamps, but not more for these pins, according to the microcontroller datasheet. And the same 2 pins actually are also the data pins for the USB port. I mean, this microcontroller has has USB capabilities, and these 2 pins are the USB data pins. So I don't know if you maybe in the future are thinking modifying the software and want to use a USB for some reason, then you have access to those 2 pins in here also. So and what else? You should use an optocoupler, like I said, but they have infrared diodes or LEDs, and then they have a voltage drop of around 1 to maybe 1.4 volt. It depends on optocoupler and who is manufacturing that and what type of LED diodes they use inside, but it's around 1 to 1.4 volts. So considering you get here about 3 volts, you can supply directly the LED from the solar BMS, but you should not use anything less than around 470 ohms in here in series. So you need to use a resistor to reduce to limit the current to the optocoupler, but you should calculate whatever current you need for that LED depending on your application, what sort of speed you want to switch that optocoupler, what type of optocoupler you have, and all kind of stuff. But I just want to mention you should not use normally anything below 470 ohms. Higher it's no problem if your optocoupler can work with that, but don't use anything less. Okay, then of course there is the SD card also in here, a micro SD slot, but this is not used. I mean, it's connected in hardware, but there is no software for it, so I think I mentioned this before. And then on the bottom in here you have the 10-pin connector, and this is you have actually the pinout printed in here. I wished I would had this connector also printed in here, but I forgot to do that. I didn't have this connector in the beta sample, and I forgot that. But you can find the pinout of this connector if you forget or don't know. You can find it in software if you go on the device setting under external 1 and 2 pins submenu, and there at the bottom you will find the pinout of this connector. So yeah, you can still find it. So the 10-pin connector, it has the first 2 pins are ground pins, and the rest starting with pin 3 up to pin 10 there are the cell voltages from 1 to 8. And then you have the 6-pin connector, which has the serial port, normally used for data logging, but you can find other uses for this serial port. It's optically insulated, so there is no problem, you can connect it to anything. And then the other 3 pins on these 6-pin connectors are the external temperature sensor, but as I mentioned before, you can use this for other purposes, like measuring an external current, for example. Maybe you want to do that, I don't know. If you are thinking of using external relays or extended capabilities of the solar BMS, then maybe you want to use this analog input as current measurement to protect for overcharging and over discharging. Not over current, and for charging and discharging. So you can use it for that, or you can use it for any other thing that you want to measure an analog value. The input is up to 1.8 volt, so 0 to 1.8. You should not exceed that. Otherwise you can damage the main IC, which is the one that measures this value. The value is measured with a 14-bit ADC, but it's rounded to just 12-bit, so that's what you have access in software to the 12-bit from this input pin. It's the pin 4, the temp E. The temp O, it's a 2.4 volt. That it's not a continuous 2.4 volt. It's a pulse every, I don't know, few milliseconds when it makes the reading. So it's exactly when it makes the reading that you get that pulse, and that it's used to supply power to if you use an external temperature sensor, which is made of a thermistor, and you also need a resistor in series to make up a sort of resistor divider, and then measure the voltage drop on the thermistor. Okay, what else? Then you have this power connector, and I get a lot of questions about why did I choose this type of connectors for the power connector, and there are quite a few reasons, but I don't even know where to start. When I firstly designed this, it was supposed to be 20 amp charging, 40 amp discharging solar BMS, and much smaller, so it should end it around here where you see this screw, and use only one of these connectors. And then I extended this to handle larger current, and then I used 2 of these connectors. But this is not the important reason. The important reason was that I wanted to have this as small as possible, and so not just as size but also as weight. And the reason for that was the shipping cost. If this will have 2 or 3 times as heavy as this one, it will have been impossible for me to ship this anywhere outside the American continent, let's say, maybe anywhere in Europe or Asia or Australia. It will have been just impossible, because the shipping will have been doubling the cost of this solar BMS. So this is an important reason, but not the only reason. Then another reason for this to be lightweight is that it can be installed on devices that need to be lightweight. I don't know, like electric vehicles, very light electric vehicles, maybe a solar powered car, or a bicycle where every gram of weight, of additional weight counts, or I don't know, maybe a large quadcopter or something like that. There are many places where the weight is quite an important factor. So I wanted to have this as small as possible, and you will see me talking about this later when we talk about the thermal design, about the size of this also. But yeah, these are appropriate for the current 80 amps can be delivered with 4 of these connectors. Each can deliver 20 amps easily, and you can use about 3mm wires, 3mm square, or AWG 12. This is the imperial units, and this the way that I can purchase cables here. So you need something like that in here, and what I will be using is this. I don't know if you can see it. This is a distribution block from I think mostly the car audio guys use this, but you can find this on eBay, maybe other places, I don't know. I got this on eBay for about $10, and as you can see, it conveniently has 2 of these. You can find this separately and in different positions, and there are many type of distribution blocks like this that you can find. But you see, I can use 4 wires from these connectors in here. So this will be mounted somewhere underneath the solar BMS. I will have 4 short wires in here, and then I can have a thicker wire, I think up to AVG 4 or something like that, that can go to battery or load in this case. So because this will be mounted here, 4 of these will be connected to load, 4 of these will be connected to battery, and then I can connect here 2 thicker wires to go to battery and inverter or whatever load I have. But and the solar will be directly connected to these pins, because like I said, each of these can handle 20 amps, and you can connect up to 1000 watt of solar panels in here. So you can connect to 250 or 240 watt panels like I have, and those deliver 8 amps each, so 16 amps in total. So it will be under the limit of each of these connectors. So I connect 2 panels in here, and in my case another panels in here, because I only have three panels, three large panels. Okay, so yeah, you can, I mean, it was yeah, $10 on eBay, and it's solid brass. It's as heavy as the solar BMS almost, so you can understand why I could not have built this small and light with such large connectors. But you can use this externally, and then there is no problem. But Anyway, the distance from the battery and from the load will never be larger than usually maybe 1.2 meters or 3-4 feet, because this needs to be close to the battery anyway and to a large load, so it will not be that far. So you can even skip that if you want, but I will be using this to connect to battery and to load. Okay, so what else? Yeah, about the size of this unit. It's about 88 centimeters wide and 120 long, and I think it's around 16 millimeters wide. Let me see if I can find a... Okay. Yeah. Okay, I will measure it for you. So I don't know if you can see it. So it's around 120 millimeters by let's see. Okay. Enough space in here. Okay, I see 87.4 wide, and thickness, it's around, now let's measure on a screw, so it's about 16 millimeters, but this includes the screw head on top, so this is really the maximum. If I measured here, it's a bit less. So okay, this is about the size of this, and just as a comparison, I will put this next to one of the solar BMS, one of the solar charge controllers that I use right now. These are for lead acid, but they have programmable parameters. So this is just a 20 amp solar charge controller, and I don't know if you can see on camera, but it's a huge size difference. Not so much in length and width, but especially in thickness. So this just looks like a monster solar charge controller, and this is just a 20 amp solar charge controller. So maybe you now have a better idea of the size of this solar BMS. When you will get your hands on it, then you will have an even better idea. And I should mention another reason why these connectors are enough is because unlike other solar charge controllers, I don't use the ground power pin to connect. I mean, they have 3 of these pins are positives from load battery and solar panel, but also they have 3 connectors for ground, and I don't have any ground connector in here. All these are positive wires from PV, battery and load. The negative, the ground, it's connected outside of this solar BMS, because I don't need the ground pin, or I actually need the ground pin to power this, but it uses very little power. So the ground is coming to this 10 pin connector in here. There are 2 pins for ground, so it's more than enough for just a few milliamps that this solar BMS is using in normal operation. So you should look at this as having just 3 pins. They have these other 3 which are just connected together inside. If this, I mean, this is this has the negative as common. Some other solar charge controllers have positive as common pin, but this particular one has negative as common, and they just internally connect these 3 pins together. But you'll have that connected outside using maybe something again similar with this distribution block, and you connect all ground pins together from PV, battery and load. Okay, and it seems this will again get a bit long, but what else I should tell you about this? I will open this for you so you can take a look inside. You probably already have seen this inside. I had a lot of photos taken and on Google Plus, and if you follow me there, and you also have seen the beta, and there isn't much difference between beta and this. I mean, there is some difference, but not that much. So in order to open this, if you want to open, I don't know, maybe you don't, maybe you want, you can do it. It's not that hard to open this. I mean, it's I should not forget to mention, this is also a development platform. It's not really a product just ready for you to use. It's something that you can develop your own product based on this. So it's a sort of development board, and it's quite modular and made easy. You should have your finger on this large connector, and then you should lift from this corner, this front panel. You see there is only one 60 pin connector in here that goes to the touch keys, and this is the front panel, nothing much to see here. Then you have the LCD. The LCD is the Nokia 5110 LCD. It's very common for DIY people or those that like to play with LCD. Is very inexpensive LCD, and was not really the best choice to get this one, but I needed this because it was low power and daylight readable. So for this particular project I needed something like that, and this has I don't know if you can see, it will focus. This has a conductive strip in here, or rubber, or I don't know how to call this, and this makes contact in here with this gold plated pads. I forgot how how to call this. So gold plated pads. Okay, you can see now much better the 5-pin connector. This was quite expensive, in fact, because it's really hard to find SMD 2.5 millimeter headers or 0.1 inch headers, and this was the only one that I found. I think it was close to $1 or something like that, and it may not seem expensive, but when you think about this solar BMS is made of almost 200 small parts. Then each parts add up quite a bit, and then in order to remove this main board, you should lift it from this corner up like this, and then you see it's the connector is in here, and it's again the same type of connector like this one. It's a 60-pin connector, and I use multiple pins for redundancy, so it's each signal has 4 pins connected, so it should be quite reliable. And This is the power board. There isn't much in here. You have the load MOSFET. This is IPT 007N06N, I think. So it's not quite hard to remember. I can think of the James Bond of MOSFET transistors. It's quite an impressive MOSFET, but also really expensive. And then you have this TVS to protect against a voltage spikes. So it's a 1500 watt TVS in here that will protect this load MOSFET. And then you have these other two MOSFETs for the solar charging part, for the charging part. And then you have the shunt resistor. One it's here, it's for the solar, and these other two are for battery. And on load, I don't measure the current for load, but I make the difference between these two in software. So what else? There is a Max 4080 in here, 4080S. I made a mistake when I ordered first time this. I ordered, I think the T part or something like that. It was just a 20X amplifier. This is just to measure the current from the solar. It's just a current amplifier, and this is a 60 times amplifier, so it will increase the voltage drop on this shunt resistor 60 times, and then it will go to the ADC input of the main IC. And from there I use the microcontroller to display the current in here. Okay, I don't think there is anything to say about this aluminum PCB, except that it is designed, it's completely flat on the back, and it is designed to be mounted on a heatsink. And maybe now it's not the right time, but I will show you what heatsink I will be using as this one. I don't know if you can see it. This is quite a large heatsink. Let me see if I can get this on camera. Normally you need only half of this heatsink for one unit to use it at maximum capability, but I will be using two of these solar BMS, one for the main battery and one for the backup battery, which by the way saved me yesterday because it was cloudy for a few days, and I was not paying attention and the battery was completely discharged, the main battery. So I was last night I was on the secondary battery. This was second time since I moved here that this happened, and actually last time that happened was last year in the same month in August. I think I don't pay attention too much on the power usage in August, so that's why I was without power. But this should not happen when I will have the solar BMS installed, which will show me the state of charge. I don't have any state of charge indication right now. Okay, but let's get back to this. Okay, if I'm here, I will probably need to continue and talk about thermal requirements of this solar BMS. The solar BMS itself, without any heat sinking, will be able to dissipate around 6 watt without overheating or anything. 6 watt of heat, and the load part is dropping about 2 millivolt per amp, and the charging part, it's dropping around 6 millivolt per amp. So you can calculate exactly how much power you will be losing in the form of heat on this solar BMS with this very simple formula. Let's use a calculator. So let's say you want to use the maximum 80 amps on the discharging part, on the load, and like I said, you have a loss of 2 millivolt for each amp, and so let's say 2 millivolt multiplied by 80 amps gives you a total of 160 millivolt drop. Okay, so 0.16 volt, which is a drop on the on this part, on the load part. Then multiply this with 80 amps, like I said before, and it gives you 12.8 watt of heat will be dissipated when you drive 80 amps to the load circuit part. So this will exceed what this can do without any additional heat sinking. And okay, let's calculate also the maximum low heat dissipation on the charging part, and there is 40 amps maximum multiplied by 6 millivolt. You get 240 millivolts, so 0.24 volt multiplied by 40, it's 9.6 watt of power dissipated on the charging part. So around 22 watt in total if you use this with 40 amp charging and 80 amp discharging simultaneously and continuously. Then you will dissipate around 22 watt, and you will need an additional heat sink that can be an aluminum plate about 4 times the size of this one used on the solar BMS, or you can have a heat sink, any type of heat sink, or you can use a fan if the weight is important. Like I mentioned before, weight can be important in some applications, and in that case maybe a heat sink it's not a good idea, and then you can use something like maybe a small 80 millimeter fan in the back of this, and that will do the job just fine. 22 watt of heat dissipation, it's not that much, but for passive cooling you need a little bit of heat sinking. And yeah, what else I wanted to say about this? Hope I don't forget anything. Yeah, okay, maybe you want to know what will be the limit without heat sinking of this solar BMS, and that's about simultaneously 20 amps charging and 40 amps discharging. And to show you that's the case, I will say 40 amps discharging multiplied by 2, it's 80 millivolt, so 0.08 multiplied with not 80, 0.08 multiplied by 40 amps, it's 3.2 watt on the load side, and then 20 amps on the charging multiplied by 6 millivolt gets you 120 millivolt, so 0.12 multiplied by 20, 2.4 watt, so it's 2.4 plus 3.2, I think 5.6 watt, so it's just under the 6 watt limit that I was talking about. So this can do 20 amps charging and 40 amps discharging without any passive and without any additional heat sinking. Okay, so I think I said what I wanted to say about the thermal management of this. What else? Yes, I need to show you the main board. Okay, you have in here the main IC. This is the ISL 94203, and with all the components around it, filters and everything else that is needed for this to work. These are the MOSFET transistors that are used for cell balancing, and this you have two in series for each cell. These are the resistors for cell balancing. This will drop all that, it will dissipate all that power from the cells to discharge the cells that are charged higher. And they seem small because these are 08 or 5 parts, but these are half watt resistor. Each is half watt, so you have 1 watt power resistor here, and I have a bit of copper here for cooling, but anyway, since this is just a maximum of 100 milliamp, what you will have maximum, depending on battery type, let's say 4.2 volt multiplied with 100 milliamps, it gets you less than half watt power dissipated, and these are 1 watt resistors, so there's no problem. And again, if we take this worst case and we have 0.42 watt multiplied by 7, because you cannot have more than 7 cells higher than then you get about not more than 3 watt dissipated on this PCB, and that's no problem for this. This can dissipate this 3 watts without problem, even if you have 6 watts dissipated in here, so that's absolutely no problem. But you can understand why the limitation. If you want to have internal inside the solar BMS cell balancing, you cannot go above 3 watt and dissipate on this PCB. It is quite a thick PCB and has a lot of copper, but it's still you cannot go above 3 watt if you don't want to overheat things. So, but again, 100 milliamps is more than enough to balance a good battery, or not to balance, to keep it in balance. And yeah, I think that's it about this part. These are the opto isolators. Like I said, I changed them. And then I have this is the quartz, the 32 kilohertz quartz for the clock. And this is the power IC. It's a DC-DC converter with very high efficiency. This is the microcontroller, like I said, STM32 F072. It has 128K of flash and 60K of RAM, so it's quite capable. And as of now, I think my software has under 80K of program memory used, so you still have enough space in here to implement SD data logging if you want, or any other things that you want to implement. And I only use just above 2K of RAM, so there is also enough RAM for the FAT file system to work on this micro SD. And I think that's it about this. I don't see anything that I want to say. These are just LEDs for backlight, for LCD backlight, and yeah, that's it. Don't want to go much further because this is already a long video. Okay, and I have some footage that I will probably include in this video at the end with how I built these 6 pre-production samples. So maybe I will include that in this video at the end. And yeah, that's it. Thanks for watching this video, and I hope I answered most of the questions. No, just wait a minute. I have forgot to mention, I think, if you want to program this, what sort of program will you want to use? And this is a discovery board. It's an older one, but you can use almost any discovery board from ST. This is just $10 or so on DigiKey or any big electronic site like that. And I probably recommend this as a programmer for this. This is what I use as a programmer for this solar BMS, and I will show you how these are connected in here. You only need 3 pins to program this. The other 2 from the 5 pin are for the external 1 and 2 I/O pins that you can use for extending the capabilities of the solar BMS. So let me show you exactly how I connected this, so there is no problem. The black wire, the one in the middle, pin T3, it's the ground. Then you have the data, the white one is the data pin, and the clock is the gray wire. And let me see if I can have this on camera. You see this first pin in here is not connected if you start from here. I don't know if that's, yeah, it's the pin 1. So pin 1 is not connected. I think that's a power or something like that. Then you have the clock, and you have the ground pin, and then you have the data pin, and in order. And then there are another two pins that are not used in this. And also you should remove all jumpers on this board. So I have it here, but it's just so I don't lose it. It's not connected. You should remove these 2 jumpers and this jumper from here. So you don't have any jumpers in here, and then you just connect this to USB, use your preferred programming application from ST, or I don't know, whatever you want to use. And then you can just maybe update the firmware, or you want to develop your own software, because this is, as you know, open source hardware and software, so you can do whatever you want, and it's a development board. So sorry, I almost forgot about this this part. So yeah, hope this was okay. What else? Yes, okay. I think I touched this subject a little bit in the first video, but this is the USB to serial converter. You will be probably using something like this. This is just like $3 or something like that on eBay. And you will have this connected on this 6-pin connector. I will not include this cable, but you can build this. I will include only the solar BMS and the 10-pin connector and cable. It will be, I think, about 3 feet of cable, or 90 centimeters. And this is just one that I made for test. I didn't purchase these connectors and this cable because I didn't plan to implement serial data logging, but I did. So software is implemented, but you will need to purchase this USB to serial converter and the cable and connector, the 6-pin connector. it's not that a big of a deal. So how do you connect this? You only need 2 pins from here, the ground, the insulated ground, the ground X, and the RX pin. It's let me see, it's pin 1, the RX, and pin 3, the ground X pin. And it's noted here as RX, meaning that you connect this RX pin to the RX pin in here, but it's actually the takes pin, the transmit pin from the solar BMS. So okay, and from here you need 3 pins. You need the RX pin, the ground pin, and the 3.3 volt supply pin. And what you do is with those 3 pins, this is the 3.3 volt supply pin. You connect a resistor as a pull-up to the RX pin. This orange pin, it's actually orange in both sides. This orange is the RX pin from serial converter, and from the solar BMS it's the same orange pin. And this one is connected together. It's the ground pin from the serial interface to the ground X pin of the solar BMS. That's it. That's all you need to make data logging on a computer. And then you use whatever serial terminal you have. If you are in Windows, I think there are plenty of options. And then I will maybe show you, if you use Linux, what sort of commands you need to do in a command line, so that you can easily save a CSV file or from this solar BMS, or watch it directly in terminal, watch the data directly in terminal. I will probably introduce a small clip or a screenshot or something in this video showing you that, probably right now. It will be on screen. Okay, I hope I don't forget during editing to do that. Okay, as a bonus, not that this video is not very long already, but here is me trying to emulate a pick and place machine. And what you see here is that I removed the front plate from the power board. I used that to glue the power connectors in, so they will not move during baking. So that's it. These are the shunt resistors that I just installed. These are the direct FET, the MOSFET for charging. Okay, this is the TVS. The power MOSFET, this is for the load, is the IPT007N06N. These are the diodes. It's just for ADC protection. And these are some capacitors. Okay, these are the 18 volt Zener diode for the gate of the MOSFETs. And also the resistors for the gate MOSFET to discharge the gate. And this is a 2.4 Zener diode. This is to protect the ADC input from from the Max 4080. These are resistors for the gate of the MOSFETs. And yeah, here is the Max 4080. And this is the 60-pin connector. Yep, that's it. The video with the power board that you just watched, that was at 4 times normal speed, and this is 8 times normal speed with the main board. These are the MOSFETs that are used for battery balance. Some resistors for the N-channel MOSFETs, the P-channel MOSFETs. The N-channel MOSFETs already have those resistors inside. It's not just a simple MOSFET, it's an IC. But it saves me a bit of work to install the additional resistors, even if those N-channel ICs are a bit more expensive because they include some passive parts inside. Okay, these are the filter capacitors for each of the 8 individual channels that measures the each individual cell voltage. Again, more capacitors. All sort of filtering capacitors. Yeah, this thing takes quite a while. I think it took me about 40 minutes, 45 minutes to populate this board, and it will not be fun at all to do the rest of the 60 boards. It will take me probably a full month to install everything. I'm trying to make it as fast as possible, but this thing, it's not fun, and it takes a lot of time. It's probably fun to watch it at this high speed. Yeah, I was just installing the half-watt resistors. I think I mentioned in the video before. Those resistors are from Panasonic. Really nice resistors because they are small and can handle a lot of power. Okay, this is a fuse, 250 milliamp fuse. And this is the DC-DC converter IC. Okay, the microcontroller. and these are the opto-isolator. (32 kHz clock and the main IC. Okay, this is the micro SD slot and the 60-pin connector. That's about it. Okay, I'm leaving you with me baking the main board, and thanks for watching this video, and if you have any questions, please leave a comment below and I will try to get back to you as soon as possible. Thanks.